Hello everyone, I'm Roggiolani and today I will present you my work, Unsupervised Pre-Training for 3D Leaf Instance Segmentation. In the last 70 years, the world population has grown from 2 to 8 billions of people, and this number is only going to increase. To face the augmented demand of resources, agriculture needs to produce more food than ever and in a sustainable way. The use of technology can help us achieving this goal without compromising on the production. One task of agriculture that can be enhanced by robotic systems is phenotyping. Phenotyping is the analysis of the visible trait of plants, which depends on their genotype, on the environment in which they grow, and on how they are managed through time. In the past, this task has been done manually, requiring workers to go into the field and measure by hand all the desired traits from plants and leaves. However, robotic systems can automatically distinguish plants and leaves and extract relevant traits that we care for. To enable machine learning models to work properly, we first need to train this model on manually annotated data. This means that we still need the workers to get into the field and gather ground truth information so that we can train our network. One way to reduce the labeling effort is to pre-train our neural network in a self-supervised fashion, so using unlabeled data. When this is done properly, the network can be then fine-tuned on our final task with less time, less label, and less effort. We propose a domain and task-specific pre-training approach. The task we target is the leaf instance segmentation task, since only after separating the plant in each one of its leaves, we can then extract relevant traits for each one of them. We use an encoder-decoder network which takes in input the point cloud, so endpoints, and for each one of the endpoints we use 6 features. The first 3 features are the X, Y, Z component, which give us the position in the 3D space, while the other 3 are the RGB values, which give us the color of the point. As output, we get a d-dimensional embedding, and one then can use these pre-trained weights to initialize the network and fine-tune it with manually annotated data. As first thing, we make our approach domain-specific, using only point clouds coming directly from the real field. This makes the network focus on relevant traits for the agricultural data. As second thing, we use domain-specific augmentations that help us simulate different realistic scenarios that can happen in the field. The first augmentation we use is to simulate wind that can distort the leaves of the plants. As first thing, we compute the center of the point cloud P as the mean of all points. Then, each point in the point cloud is rotated around the 3 axes with a magnitude that depends on its distance from P. The rotation of the farthest point is sampled from a uniform distribution between 0 and a maximum, which is a user-defined input. We can see in the image that the points in the blue area are more rotated than the points in the orange or in the pink area, and most of all the points around P are basically left untouched. When we apply this transformation to a full plant, P usually falls into the stem region, thus giving us the maximum rotation for the tips of the leaves. The second domain-specific augmentation we use is to simulate occlusion. This can happen since plants are sown in rows, and at later growth stages, plants from adjacent rows can overlap onto the current rows. What we do is we generate an ellipse whose width and length are sampled from a uniform distribution where the maximum and minimum value are user-defined inputs, and then we erase all the points that are falling into the ellipse to simulating the occlusion. As last thing, we make our pre-training task-specific. The leaf instance segmentation task requires us to assign a unique ID to each point, where each ID represents a leaf. However, in the unsupervised setting, we do not know how to enforce this, since we do not know which points belong to which leaf. However, we can enforce that close points have a similar embedding, while faraway points have a more faraway embedding. This is because closer points in the 3D space have a higher probability of belonging to the same leaf. To do so, we use a distance-based similarity matrix in our loss that help us pull together embeddings of close points and pull apart embeddings of faraway points. However, we cannot use the Euclidean distance to compute this matrix, since, as we can see in the image, points that are closer in space, like P1 and P2, may actually belong to different leaves, while points that are far away in space, like P2 and P3, may actually belong to the same leaf. To overcome this problem, we use a graph approximation of the geodesic distance computed on the surface of the plant. As last thing, we also propose a domain-specific clustering. As we can see in the image, we cut a circle from the center of the plant, so clustering as first only the tips of the leaves. This is done because the center of the plant is the hardest for labelers to label, but also for the network to predict, since most of the leaves are coming together into the stem. Then we iteratively reduce the radius that we are cutting and use the previous iteration as initialization for our clustering, until we reach the end where each point in the point cloud has been assigned a unique ID. In our experiment, we show that our pre-training boosts the results over multiple backbones, and most of all, it halves the need of labels to obtain the same performance of the network without any pre-training. We also show one qualitative image coming from a point cloud gathered on the field. And in our paper, we also show the performance of our post-processing approach compared against state-of-the-art clustering algorithms. In conclusion, in this presentation, we show our domain and task-specific pre-training that works on multiple backbones and halves the need for labels for performing the leaf instance segmentation task in 3D. If you are curious about our approach, feel free to contact us, or you can use the QR codes to check our paper and our open source GitHub implementation. Thank you for your attention.